Welcome to Noise Control Fundamentals. In this module, we're going to explore the importance of understanding noise control and how it relates to air distribution. Noise control can be just as critical as environmental conditioning when it comes to air conditioning systems. Human comfort is greatly affected by the noise levels in the environment. Too much sound or unwanted sound can create unpleasant living conditions, but the absence of any sound can also create uncomfortable conditions for the occupant. The right mix of sound can cleverly mask unpleasant noises such as conversations, computer equipment, and office machinery. To obtain the proper level of sound in a room, the right ventilation system must be selected and tested to ensure the optimal level of comfort is achieved. In this section, we will learn exactly what sound is, how we measure sounds in our environment, and how to add sound sources. Once we understand the basics of sound, we'll then look at testing, the price testing facilities, and the importance of properly configuring a room with air distribution equipment in order to achieve the maximum level of comfort. What is sound? The range of hearing for the human ear is extremely broad. We can hear sounds as low as a blade of grass blowing in the wind to the roar of a jet engine as it takes off. Sound is an active part of our everyday lives. Sound can be pleasant and provide comfort and relaxation, or it can also be considered a nuisance or a disturbance. Sound is basically any pressure variation that the ear can detect. These pressure variations are caused by a vibrating object or surface, or by turbulent air or gas. Noise, on the other hand, is any annoying or unwanted sound. What differentiates a noise from a sound is subjective, but is often due to its volume or tonal qualities. If we can determine what differentiates sound from noise, we can better address the issue of noise control. And to do this, it's important that we understand how to measure sound. Measuring sound. A pressure variation in a sound wave can be measured in micropascals to determine its loudness. The greater the pressure variation there is in a sound wave, the louder it'll be. The micropascal is an actual physical measurement of the pressure variation in a sound wave. The weakest sound detectable by the human ear is 20 micropascals. To put this into perspective, a pressure change at this level causes the eardrum to displace less than the diameter of a hydrogen molecule. At the same time, the ear can also withstand pressure changes more than 1,000,000 times this lower threshold. This type of measurement would result in a rather large and awkward scale. To avoid this, another scale is used, the decibel or dB scale. Compared to the micropascal, the decibel scale gives a much better representation of the way humans perceive relative loudness. This is because the ear does not react proportionately to changes in volume level, but does so according to a logarithmic scale. Note that while the micropascal scale is a literal, linear measurement of sound pressure, the decibel scale is more compressed and focuses specifically on the human range of hearing. Please experiment with the following interactive screen to better understand sound levels. There are some important things to remember about decibel measurements. A change of 3 decibels is barely noticeable. This is the point at which the human ear recognizes a change in volume. A change of 5 decibels is a clearly noticeable change. A change of 10 decibels appears to be twice as loud as the original sound. Frequency. Frequency, which is measured in hertz, is the number of pressure variations that occur per second in a sound wave. The sound's frequency produces a distinctive tone. This is why a flute, which has a high frequency, and a bass drum, which has a low frequency, sound so different. The range of human hearing is anywhere from 20 hertz all the way up to 20 kilohertz. The human ear is most sensitive to sounds between 2 kHz and 5 kHz. Please experiment with this interactive screen to better understand frequencies. Adding sounds. Because the decibel scale is logarithmic, the addition of sound levels cannot be done directly. Let's take a look at the concept of adding sounds. The following formula can be used when combining sounds. Press the Solve button to see the solution. Alternatively, the following chart can also be used to determine sound totals in decibels. At the bottom of the chart is the difference between the two sound levels to be added. The numbers found on the left side of the chart represent the decibel level to be added to the louder sound source to arrive at a decibel total. To better illustrate adding sound levels using this chart, let's take a look at a couple of examples. Take, for example, this mixer, measured at 65 decibels, added to the blender measured at 70 decibels. The difference in the two sound levels is 5 decibels. We find that value at the bottom of the chart and extend a line from this value upward and across the chart. The resulting number, 1.2 decibels, is then added to the sound value of the loudest source for a total sound level of 71.2 decibels. In this example, both hand drills have sound levels of 75 decibels. The difference in the two sound levels is 0 decibels. We find that value at the bottom of the chart and extend a line from this value upward. The resulting 3 decibels is then added to the sound value of either source for a total sound level of 78 decibels. Take, for example, this radio, measured at 75 decibels. Added to the lawnmower measured at 85 decibels. The difference in the two sound levels is 10 decibels. We find that value at the bottom of the chart and extend a line from this value upward and across the chart. The resulting number, in this case 0.4 decibels, is then added to the sound value of the loudest source for a total sound level of 85.4 decibels. Here are some rules of thumb to remember when adding two sound sources measured in decibels. If the two sound sources are equal, the resulting total will be 3 decibels higher than either of the measured values. If one source is more than 10 decibels greater than the other, the quieter source's contribution can be considered imperceptible. Remember that when adding two sound sources measured in decibels, the total will never be greater than 3 decibels higher than the loudest source. As you may recall, a 3 decibel change in volume is barely noticeable to the human ear. Sound power versus sound pressure. It is important to understand the difference between sound power and sound pressure when considering the measurement of an object's sound energy. Sound power is the total sound energy of an object, independent of any environment. We typically determine an object's sound power in a room with no dampening influences. Wherever possible, sound power levels are given for HVAC products to enable reliable side-by-side comparisons. Sound pressure is a measure of an object's sound level in an environment where dampening influences are an issue, such as wall hangings, carpeting, and furniture. Although catalog data provides a basis for product comparisons, the environment into which an HVAC system is installed can greatly affect noise levels perceived by its inhabitants. In order to understand the difference between sound power and sound pressure, let's take a look at 3 similar scenarios. Consider the analogy of a heater's warming effect on a room. The heater's heat output or power is rated in either watts or BTUs. This power output will remain constant. We can measure temperature at any point in the room with a thermometer. The size of the room and how it's constructed and furnished will influence the heater's effectiveness, but it will not change the heater's power output. Well-insulated walls and well-designed windows will help maximize the heater's efficiency. Your location and distance from the heater will also influence the temperature that you record. In this instance, we place a light source in the room. The light's output is rated in either watts or lumens and remains constant. The illumination can be measured with a light meter. The size of the room, its construction and furnishings can greatly influence the light's effectiveness. Light-colored walls and furnishings will tend to reflect light back into the environment, while darker colors will tend to absorb the light. Your location and distance from the light source will also affect any readings you might make with a light meter. Finally, let's apply the same scenario to a sound source. The object being tested has a certain sound power level. This sound power level can be expressed in watts or decibels. Sound pressure can be measured with a VU meter. The sound pressure levels recorded are greatly affected by the room. Cement, glass, and tile surfaces will tend to reflect the sound back into the environment. Items such as furnishings, wall hangings, and floor coverings will tend to absorb sound. Your location and distance from the sound source will also influence the sound pressure measurement that you make with a VU meter. From what we've explored in the previous three analogies, we start to understand that the term power is always associated with the energy emitted by an object. Therefore, sound power is the total sound energy of an object, independent of any environment. Sound pressure is a measure of an object's sound level in an environment where dampening influences are an issue. Testing. The availability of reliable sound power and pressure data is important when it comes to comparing and choosing specific products suitable for an environment. A key element in the Price Test Facility is the reverberant sound room constructed to meet ASHRAE and ISO test standards. It is used to measure sound levels produced by the various Price manufactured products. These readings are made under carefully controlled circumstances so as to determine the amount of noise produced by the item in the absence of any dampening influences. Sound absorption in the room is minimized by the specially coated walls and concrete construction. Background noise checks and regular calibration ensure that testing is done in a consistent and precise manner. The resulting sound data is published in the Price Air Distribution Catalog in order to help you select the right products for the right environment. Please explore this interactive screen to see the various components of the Price Reverberant Sound Room. Frequency Analyzer. Utilizing Brielle & Kjaer's state-of-the-art dual-channel real-time frequency analyzers ensures the highest accuracy of sound measurement available. Pressure gauges. Airflow and pressure measurements are recorded in accordance with industry standards, utilizing precisely calibrated meters and gauges. The sound room door is acoustically lined and constructed of metal. We use two separate doors with gasket seals to ensure a sound-tight environment. Calibration. Frequency analysis equipment is calibrated using a known sound source. Air supply and test subject. Air is supplied at precisely controlled rates to the test item. The room is outfitted with relief silencers which allow air to escape the room but prevents any noise from re-entering. Walls are constructed from concrete with a plaster coating and covered with an epoxy paint. By using the hardest surface possible, we maximize the amount of sound reflection in the room. The room walls are also constructed to meet specific height, width, and length requirements. Microphones. 3 microphones are placed in precise locations in accordance with ARI testing procedures. The microphone configuration ensures a representative sampling of all frequencies and sound from every direction. As you may recall from our previous chapter on frequency, Frequency is the number of pressure variations per second in a sound wave. Although it is important to get an idea of how loud a particular product is, it's also useful to know what frequencies it produces. Unlike a musical instrument, which produces a specific note, a device such as a terminal unit, fan, or diffuser will simultaneously produce a vast variety of frequencies. For instance, a fan might produce a lot of low-frequency noise due to its motor. High-frequency noise might be produced by airflow through dampers or diffusers. The normal range of concern for most air terminal devices is in the 90 to 5600 Hz range. To derive frequency-specific test data, electronic filters are used to isolate noise occurring in the following frequency ranges. Note that each of the frequency bands center on a frequency which is double that of its predecessor. A tone with a frequency that is twice that of another is said to be 1 octave higher. The frequency ranges that we analyze are therefore called octave bands. Because the contributions found in octave 1 and octave 8 are often imperceptible in HVAC applications, we discard the data found in these frequency ranges before publishing results in the catalog. Once the original sound has been separated into frequency bands, we can then measure the loudness of each one independently. Please experiment with this tool to hear the kinds of frequencies that we analyze in our testing facility. NC levels. An NC value is the result of reducing all of the sound power data for a specific product into a single number. To accomplish this, we first estimate the sound pressure that an occupant will experience in an environment. Given that we can't predict how the product is going to be used, ARI has determined a conversion process that assumes that the device is installed in a typical room. Attenuation values provided by ARI are subtracted from the sound power levels determined during the frequency testing. This conversion accounts for various environmental effects that will attenuate or dampen the sound. Let's set these values aside for just one moment. If we take the adjusted figures from our octave band tests and plot them on the graph, we can determine an NC rating for the device. The lowest NC curve under which all of the test data fits is considered to be the device's NC rating. An NC rating is a single number that represents the perceived sound level of a device and is commonly used to rate noise levels of air distribution products. The catalog and selection. How do we determine whether a product is acoustically suitable for a specific environment? Sound power data and NC ratings for most products are readily available in the price catalog. Let's take a look at how this information is presented and how we can use it to select products for a particular environment. As you may recall, we placed the device to be tested into the reverberant sound room. Sound data is presented differently in the catalog for GRDs and terminal units, so for this example we will examine the discharge sound from a terminal unit. Most devices are tested by passing air through the device at various predetermined rates and pressures. The sound produced is picked up by the microphones and fed into the Brüel and Kjaer real-time frequency analyzer to be split up into octave bands. We determine the sound power produced by the terminal unit in each of the octave bands and publish the information in a format similar to that shown. We determine sound power ratings under a variety of airflow and pressure conditions. Note that as we increase airflow through the terminal unit, the sound power levels increase. Likewise, the tests for static pressure drops show that as air pressure increases, sound power levels also increase. Various sizes of a product are given as well. Typically, a larger version of a particular product will be able to handle larger volumes of air without causing a significant increase in noise. Here we show a typical sound power table for terminal units that might be found in the price catalog. For any given octave band sound power test, We can estimate sound pressure levels using this ARI conversion table. It assumes that equipment is being installed into what ARI has determined to be a typical room. We use the air capacity of the device to determine which numbers to subtract from the octave band sound power values to arrive at an estimate of the unit's sound pressure levels under typical circumstances. If we take the adjusted figures and plot them on an NC graph, the lowest NC curve under which all of the test data fits is considered to be the terminal's NC rating. Because we have sound power readings for various airflows and pressures, we can produce NC ratings that correspond to each of these combinations as well. This is a portion of a typical chart found in the price catalog, which shows NC levels for a terminal unit under various conditions. Dashes are shown for circumstances where the NC level is less than 20, since the noise contribution would be so quiet as to be imperceptible in most settings. These figures appear in the catalog in typical selection guides for terminal units. Similar data appears as performance data for GRDs. Note that when it comes to HVAC products, a device with a given sound power level may be suitable for some environments but not others, depending on the reverberant characteristics of the room and the client's needs. How do we know which products are suitable for a particular environment? ASHRAE publishes guidelines that indicate what NC levels are allowable for specific applications. If we compare the NC levels given in these guidelines to the NC levels published in the catalog, we can find products that are suitable for most any room. Configuration. Now that we understand the fundamentals of sound, let's take a look at applying these principles to noise control in an air distribution environment. When designing an HVAC system, the designer must be aware that noise can be transmitted to the environment via multiple paths. In addition to the noise produced at the air outlet, noise produced by fans and dampers can be transmitted through the ductwork itself or radiated via the ceiling cavity. An improperly designed air distribution system can generate unnecessary turbulence and noise in the occupant's environment. Here are some of the more common mistakes that can contribute to a less than perfect sound environment. Scenario 1. Poor selection or undersizing. If a diffuser is too small for the volume of air flowing through it, it will create excessive turbulence and noise in the room. By correctly choosing the right size of diffuser, this problem can be avoided. Use your price catalog to refer to sizing data and NC levels. Scenario 2. Improper installation of flex duct. Another factor that can contribute to poor noise levels in a room is the improper alignment of diffusers to the supply ducts, especially when flexible duct has been used in close quarters. Skewing or crimping the flex duct by half a diameter can add up to 15 decibels to the manufacturer's noise rating. By placing the diffuser directly under the takeoff and straightening the flexible duct connector, noise levels can be minimized. Scenario 3. Straight branch length. In an ideal situation, the diffuser should be situated directly at the end of a significant length of ductwork. Should conditions not allow for this placement, an imbalance in the airflow may result. Excessive air velocity through parts of the diffuser may add up to 12 decibels of noise to the rated NC level of the diffuser. An equalizing grid may be inserted to rebalance airflow through the diffuser and decrease noise. A general rule for placing any transition such as elbows, T's, and adapters in ductwork is to give at least 3 duct diameters of distance between any transition and a diffuser. Scenario 4. Poor duct design. If a diffuser is located too close to the terminal unit, damper and fan noise will be transmitted to the environment via the ductwork. It is recommended that there should be at least 3 duct diameters of distance before your first diffuser is placed. A reasonable amount of line ductwork should be used to dampen noise. Scenario 5. Damper placement. Because dampers create turbulence and noise, it is important to position them as close to the branch or takeoff as possible. The further away the damper is located from the diffuser, the better. Scenario 6. Line diffuser plenums. Care must be taken when lining diffuser plenums. Excessive lining in a slot diffuser plenum can decrease volume, increase air velocity, and may actually introduce significant noise. Price manufactured plenums contain an optimal amount of lining so as to minimize the amount of noise produced. Acoustic mock-up room. In order to demonstrate and experience real-world scenarios, Price has constructed a test room specifically for conducting acoustic mock-up tests for terminal units. The room has been designed and finished in accordance with Acoustical Consultants Guidelines for simulating actual office acoustics. Mock-ups can be developed for each project's unique specifications, including terminal unit type, size, air volume, ceiling construction, etc. Acoustic mock-up tests are a very effective method of verifying room NC levels as opposed to relying on the theoretical calculations for terminal unit applications. Visitors can listen to the system in operation as well as be provided with sound measurements. Noise control is a very important factor when considering an HVAC configuration. We hope that you've enjoyed this overview of noise control fundamentals. Please refer to the engineering section of our Price catalog for more in-depth information into product-specific areas of noise control. Contact your local Price representative or visit our website at www.price-hvac.com for more information.